Hey Sean, are we all ready to go?
Oh yeah, just give me a minute. I
Okay.
just have to type this.
All right.
Should I share the screen now?
Yeah.
Okay.
So are you ready to start? I'm
Wait,
already taping. So good evening, everyone. This is Evergreen Valley College Academy piloting with high school students of several schools, I think. No, or just Evergreen High so far.
Well, technically we have 3 other schools.
Oh, technically we have 3, but presents right now only Evergreen High. Is that correct?
Yeah.
Okay, that's a good start. And today we have Sean Selva Murugan.
Yeah.
Hey guys, I'm here.
Talking about Herbig AB stars. And there you go. Fire it up.
Okay. So let me see. Okay, so should I start now?
Yeah.
Okay. Hi everyone. My topic is on Herbig AE and BE stars. So let's start along. So what is a Herbig AE and or BE star? So basically, this type of star, I'm just going to call it AB, is a pre-main sequence star, like T Tauri stars, except for the fact that they're a lot heavier than T Tauri stars. They range, they have masses from 2 to 8 solar masses, whereas T Tauri stars have masses that range from 0.5 to 3 solar masses. And because of their heavier masses, they have smaller lifespans, usually less than 10 million years. And also because of their masses, they usually have they contract a lot more under their gravitational pressure, and then that kind of like releases a lot of energy. So you have high luminosities and temperatures, and so for that reason, these stars are classified as spectral types of A or B stars. So as you can see here on this chart, they usually have temperatures that range from 7,500 Kelvin to 2,500 Kelvin. For a comparison, the surface temperature of our sun is around 5,000 to 6,000 Kelvin. So yeah, these pre-main sequence stars are a lot hotter than our own sun. So there are some characteristics of AB stars that we should all know. For one, we know that these stars produce mostly hydrogen and some traces of calcium emission lines. And we use a Balmer series to detect the presence of hydrogen. I'll kind of go over that in the next slide, like trying to describe how we collect all this spectroscopic data and such. Also, these heavy stars are usually located within dark interstellar clouds, and because these clouds are very opaque, it's kind of difficult to see the star forming. Usually, when these heavy stars form, they produce a lot of radiation, and that radiation kind of impinges on the cloud, and then that kind of makes it a more opaque to like the visible light coming from the star, so we really can't see it with our visible light spectrums and stuff. And also because the radiation heats the gas and dust in these interstellar clouds, we see a bunch of excess IR radiation from the circumstellar dust. So whenever we take these spectroscopic measurements or like these photometric measurements, we usually see like a bunch of static and stuff. That's basically like the IR radiation that's like impinging on our detectors, and that IR radiation is coming from the circumstellar dust that surrounds the star. And another thing about these Hades stars is that they usually form in the presence of at least one companion star. So usually, whenever we have stars that are at least like 5 to 8 solar masses, we know for sure that there must be a companion star, because you wouldn't normally have stars that start out with eight solar masses under normal conditions, right? Usually you have mergers that happen like between interstellar clouds to produce one huger cloud, and that huger cloud kind of collapses to form that 8 solar mass Hades star that we were talking about. And also we can tell that these stars are usually located in open clusters. So open clusters are usually characterized by not a lot of stars, but then like these stars are pretty bright and such. I think I forgot to put a picture of that. Let me just search that up. Cluster. So basically, this is a picture of an open cluster. I think this is the Pleiades cluster. Yeah, I think it should be.
Yeah. So
basically, there's like a bunch of bright stars. There's not a lot of them. Like in here, this is a globular cluster. I think this should be a globular cluster. I have no idea why it's in the open cluster section. But yeah, unlike these globular clusters, they usually have like very few stars, but they're all very bright. And as we know, a Hades star is very bright because we know that they have spectral types of A and B. So yeah, so Hades stars are in open clusters. That's pretty much what I'm trying to say. So back to the presentation. So yeah, so this is a Hades star, HD 250550. This is some spectroscopic data that we took of it, and as you can see here, there's like a bunch of static here and such, and then all of a sudden, like at around this 6,550 angstroms, you see like this spike that shoots up, and whenever we see these spikes that shoot up, we call this like an emission line, and this sort of spike is usually like kind of associated with hydrogen. So whenever light from the star so like, and it kind of makes sense that there's hydrogen, like we see these hydrogen lines coming up because the stars are mostly made up of hydrogen, right? And the clouds that they're surrounded by are made of hydrogen. So when we see like these hydrogen lines spiking up, we can tell that there's like a star being formed, and intense radiation is coming out, which impinges on the hydrogen particles and such, and then like a bunch of stuff happens, and then we see this. So yeah. So energy production in Hades stars. So our normal stars in the main sequence produce energy through hydrogen fusion, where you have like two protons that come together to form deuterium, and then those two come to produce helium, and in the process, you release like a bunch of energy. So that's pretty much hydrogen fusion. But because the stars are pretty young, they go through something called gravitational contraction. The fancy word for that is Kelvin-Helmholtz. And this is common for all stars during their pre-main sequence stars, and especially T-Tauri stars. So basically what happens is that the star shrinks in size due to gravitational pressure. So here you can see like these arrows pointing inward, suggesting that like there's like the mass at the top of the surface of the star kind of collapses inward. So like all mass tends to collapse inward. But then because of that, in order to counteract that whole gravitational pressure thing, you kind of have radiation pressure that kind of moves outward to counteract the gravitational pressure. And then doing so, it releases a bunch of energy in the form of EM radiation. So basically, we have gravitational potential energy, and then that gets reduced and converted to thermal energy, and that thermal energy is emitted from the star in the form of EM radiation. And that's how. And then like stars that have huge masses, like AB stars, tend to have huge luminosities because these stars, because of their high masses, these Hades stars are contracting at a faster rate than T-Tauri stars, and so and because they're contracting at a much faster rate, we see like a huge explosion in the amount of thermal energy that they release, and so they have these really huge luminosities. And because they have really huge luminosities, we can also do some calculations and find their temperatures. So Hades stars have higher temperatures than T-Tauri stars on their surfaces. And again, to recap, high mass equals high luminosity, and that leads to high surface temperatures. But also, there's also something else. Because these Hades stars are contracting under their gravitational pressure at a much faster rate than T-Tauri stars, this also means that they quickly reach their main sequence phase, and that's when hydrogen fusion starts. And usually hydrogen fusion initiates when the temperature of the core is about 15 million degrees Kelvin. And the reason for that is because when you take two protons together, they're usually repelled by the like charges on each of the protons. So if you have one hydrogen proton here and another one here, wait, let me just use that annotating thing. I can't do that. Wait, I don't think I can. Anyway, so like if you have one proton here and another one here, usually because they have the same positive charge, they tend to be repelled by one another, and so they won't really collide with each other. But then, like, as you increase the temperature of the core, the velocity of each of these protons like continues to increase. And so if you have enough of a temperature, then you have like enough of a velocity so that these two protons can collide with each other and overcome the electrostatic repulsion between the protons. And so that's how you get hydrogen fusion, and that's when this AB star enters the main sequence stage. So the role of AB stars in star formation. So the thing is, it's pretty hard for us to observe high mass protostars, like stars that are heavier than AB stars, like over 8 solar masses. And the reason is that there's usually like a lot of interstellar gas and dust covering the star, and that those heavy protostars are creating the material at such a huge rate that they go through the PMS stage very fast. So it's kind of hard to catch a lot of heavy mass protostars going through the PMS stage like right now. But with these Hades stars, scientists think that they can provide the link between the low mass T-Tauri stars and high mass protostars, because they think that there might be other processes that might help heavy mass protostars form. So yeah, and I have like a bunch of links that you guys could look up should you ever be curious to find out. So this link has like a bunch of stuff that if you're really interested about, can read on. Like it has a bunch of pictures too. Wait, if I can scroll down, right? So you can see a few examples of what are images of these Hades stars look like. As you can see, they're really obscured by all gas and dust, and that's kind of expected because we are talking about stars that form and are very huge. So yeah, and then there's a bunch of other links too. So yeah, that's my presentation.
Nice. That was a nice overview, including the profile you show. Any questions? I can see Rohit Chopra, technically. Hi, Rohit. Have any question? Comment? All right. Philip, any connection to your T-Tori stars that you could find? I would like you to show the profile, the H alpha profile in red.
Which slide is that? This one?
Correct, yes. So if you all see, this is a hydrogen line, it's a H alpha, Balmer alpha line. And this is one of the classical profiles called P, like a P sign profile, which always come with a heck of emission in the right hand side and an absorption in the blue part of the spectra. So you have more of emission and the towards lower wavelength you have this absorption. So while you were giving your talk, I kind of pull up some images, and I would like to show that to you.
Okay.
So I have to kind of share my screen. So you have to unshare your screen, and then I will share my screen. There you go. Can you all see this? Okay, so here is a star, and then you have an envelope. So this envelope is not the stellar atmosphere. It's something that's above the atmosphere. And in this example, this is not an example of a He-B stars. It's just any star that has an expanding envelope. Could be a star that is losing material. Could be a B star that is losing mass because of some radiative process going on in its envelope. So, but these cells represent cells where gas is producing some sort of emission. And so here's the line of sight, so which means you have your telescope somewhere in here, and you are observing this star. But see, the part of the shell that you see first is a part of the shell that is moving towards you. You got that?
Yeah.
And so since this shell is expanding and moving towards you, now you have Doppler effect process taken care of. So if there was no expansion, which means if you get rid of all these arrows indicating expansion, so you have just a shell, stationary, and so like an aura, right? So if you like mystic things. So you have a star and you have a shell that is not moving. And the shell is emitting light and emitting Balmer hydrogen light or transitions. So what you should see, if every single photon or every single cell of gas in this envelope, if every single cell is emitting a little line emission, a line profile, so when you add this up, you should have a nice broad symmetric profile. Now, if you add expansion, so see what happened. The part of the shell that's moving towards you, is slightly blue shift, right? And the part that moves away from you is the one red shifted, um, and you see that with the component in absorption as a result of the star itself um, that is blocking from view that radiation that is going away from you. So you have a blocking produced by the star. Um, so this is the classical P-sign profile, and that's what you show and indicate. So when you look at this type of profile, you say, hey, there is expansion going on. So this star, this Herb EB star that you show is pretty much indicating expansion of shell. Now there is another type of P-sign profile that is called inverse P-sign profile, where the absorption now is on the towards longer wavelength. So in this type of scenario, the situation is different. The part of the star, the part of the emission shell that is that appears in emission is the one that is, for instance, this is an absorption that is towards longer wavelength, and this type of inverse P-sign profile indicating fall. So you have gas falling towards the star instead of being expanding. So when you see in T-Tauri stars or in Herbig stars, this type of profile is a telltale the star is undergoing infall. So there is infall either from the disk or from the circumstellar environment towards the star. Okay. Back to your. So I'm getting a sign here that my meeting will start in 10 minutes.
Okay.
So, which means I think I would like to propose I will stop this meeting and open another meeting. You guys log in again because I would like to propose some couple of projects if you guys could work on it, and then next week we talk about it after the talk. Is that okay?
Okay. I think some of us have questions.
Yes.
They're not exactly related to what you talked about, but more about the presentation.
Okay.
So Pranadi asked a question. It was about why stars are named by numbers and not by actual letters, like words.
Hello? Hello?
Yeah.
Can we start another meeting because it has 5 minutes or 6 minutes?
Okay. Sure. Can you post a
meeting? Which means this is not working. We should have a platform that allows us to stay together without interruption for 1 hour. I like Zoom.us, but this is not working. So let's start. Let it open again, and I will try to work on some different platform for next week. But right now, I will close this meeting and then start another one. All right.
Okay.
All right. Hey, Pranati, can you hear me? Yes, the same ID number. I have Pranati there, Gaurav Desali, and that's it. Okay. So, are you guys more in computer or more in material search?
Probably more computer.
Computer.
Yep.
Yeah,
Okay.
same here.
Same there. Computer.
Yeah, computer.
Okay.
Laptop, rather.
Okay. So, you like to do image development and simulations and things like that.
Yeah, I can look up how. I can look up on that. I can read up on some of that.
Okay. I have a couple of ideas. Let's wait Sean to come back, and then I would like to mention those two ideas. It could be a long-term project during this month of August,
Okay.
And use your free. Are you guys taking any class now? I know Pranati is taking astronomy class, right?
Actually, it's over.
Oh, it's over. Now you guys have free time, right?
Yeah, but well, school starts next week.
Oh,
Yeah.
oh Lord. Okay, all right. So we do what we can. Okay, Sean, you're back. Very good. All right. So, Sean, you were saying there were some questions.
Pranati, you had a question, right?
Okay, go on, Pranati.
I don't actually.
Oh, okay.
Oh, you don't have a question?
Oh no, I was just asking. Like you said, you had a problem with Zoom, so I was just wondering what happened to CC Confer.
I don't remember exactly why we didn't like CC Comfort. I mean, it works great for me. I mean, it gives. I mean,
It was a little laggy on our side.
Yeah.
it allows me to share my screen, and I think you guys can share your screen as well. So let's. I'm gonna set a CC Comfort meeting ID number and send it to you. Send it to Sean. Sean can export to the rest of the class. But yeah, let's use CC Confer because it's better not to be interrupted.
Okay.
Okay. I have a Sean. Would you like to say something more?
On and Gaurav had a question too.
Yeah.
So Gaurav, if you could.
Oh, okay. Well, I was just wondering that so when the star goes from the gravitational, like the energy thing, to the PMS, does like it's radiating like the EM waves, and does it change to something else that is radiating, or it just continues with EM waves?
So basically, what's happening is that when the star contracts, the star actually loses gravitational potential energy. So
Okay.
say if you consider a point on the surface of the star, right?
Yeah.
And if it's contracting under the pressure of its gravity, right? That point on the surface of the sun is the star is going to move closer to its center of mass, right?
Yeah.
And so in that way, it's kind of losing its potential energy, right?
Yeah.
But like conservation of energy and all of that.
Yeah.
Right?
Yeah.
So that gravitational potential energy has to go somewhere. So it goes into heating the core of the sun.
Okay.
Right? And that's how you get your thermal energy. The particles and like the atoms and molecules in the core get really excited. They start moving around. And as they move around, they kind of let go of that thermal energy, heat in the form of light radiation, right? EM radiation, light.
Yeah. Oh, I see.
Right? And because these things are really huge, the core is the heavy stars, at least, because they have like huge masses. Star contracts at a even faster rate, and also because the cores are really large. You have more particles that are becoming excited. That means you have more energy that's being released from the core in the form of EM radiation, and so that's why these heavy stars are a lot brighter than your normal T-Tauri stars, and they have higher surface temperatures.
Wait, so do they have? Oh, so that's why they have the lower lifespan, huh?
Mm-hmm.
Okay. Okay. Cool. Yeah. All right. Thanks.
Yeah, lifespan is controlled by the stellar mass. Low mass stars, they contract slowly, take time to initiate fusion reactions, and spend longer time in the main sequence, and as opposed to the high mass stars, they go too fast through all these earlier phases, and also during the main sequence phase.
All right. Thank you.
Yeah.
So I just finished the computer science class from Professor Eisenberg.
Yes. So you guys are all good with Python, huh?
Python, yeah.
Python. Okay. So I have a couple of ideas. I was talking to Sean, and Sean thought it was a good idea, and might fly. And I know how bees you guys are, or not. So I don't know. But I would like to propose a couple of projects that involves simulations and modeling. And and this is not scientific research yet, so I don't have a star, don't have a project yet on view. It's just for fun. It's a way to illustrate what Philip talked yesterday with respect, or last week with respect to Titori stars, or what Sean is talking today about Herbig stars. In fact, I got an idea with your presentation. So let me see if I can share this file here. See if you guys can see that. Where is my Zoom? Now I lost the Zoom. It's right here. And share the screen and page. Share. So the first project is very simple. It's based on photometry. So pretty much. Oh, wait a second. Now I don't have my Zoom. Wait a minute. So can you guys see what I'm doing here?
Yeah.
Okay. So the first one is photometry. So let's say three of you. I mean, I have six students or seven. So let's say we divide in two groups. One will tackle photometry, and the other one tackle spectroscopy. So what photometry should it be? So let's say you have a star that has a very nice and uniform atmosphere, right? And this atmosphere emits radiation, and then you have your telescope, and you detect this radiation, right? And then you do a routine observations over time, and then if you plot flux in units of energy, ergs per centimeter square per time. So if you plot the brightness of the star, so you get something that is pretty much constant if there are no features in there, right? Because the star supposedly is not varying. So let's make a perfect star. Now, what if now the star has spots? So let's say you have a star that has 6,000 degrees, 6,000 Kelvin temperature. And so then you'd have a flux. Let's say you are observing this flux in a given region, right? And since the star is a perfect black body, you should be able to get certain amount of take the peak flux of that star, and should be always the same because the star is perfect. But let's say that now you have a spot that comes out, and just to make our life simple, let's start making the spot a perfect circle, and the star is also flat. So the star is not a sphere, it's flat, right? And then, so what type of signature would you observe if the spot change position as the star rotates? So the star is rotating from west to east, and so what should be now the variability as the spot goes in view? So you have some nice flux. So if you are plotting flux per time, you have a nice constant flux, and then suddenly the spot comes on view, and then what happened? What happened? Oops. There you go. So what happened? So what I would like you to do is to simulate that. How can you do that? Let's say you have a spot that is a circle. So the star has a radius r, and you can probably come up with a flux that is equal to sigma T, the temperature, to the fourth power, right? That's the integrated flux of a black body, uh, which we are assuming this star is a black body. So let's say you have a spot that is a perfect circle, and the circle has a radius. Let's say the let's think the star as being the sun, has the solar radius, and the spot is the size of Earth, is a tenth of the stellar radius, right? So this spot has an area. Do I have an eraser? Yes, I do. Oh, but it's not erasing. There you go. This spot has annotate. This spot has an area that is equal pi times radius square, and r is, let's say, a tenth of the stellar radius, because this spot is supposed to imitate Earth, size of Earth. So what would be the integrated flux now? Assume this spot is from a gas that represents a black body radiation, not 6,000 Kelvin, but 4,000 Kelvin. So the flux of this spot is going to be also sigma T to the fourth, which is 4,000, not 6,000. And but what would be the final flux? What would that be? So I would like you guys to work on it and provide a graphic of that. So certainly as the spot goes on view, so if you go down, if you have the star and the spots start coming on view, so first you don't have anything, right? And then you start appearing something, and then finally you have this spot entirely on view, like a perfect circle. So once you resolve that, it would give me a flux variation over time as the spot transit or pass over the stellar disk. On a following situation, on a next development, let me see if I can I mouse now? I think that's what I want to do. Oh, it doesn't go down. How do I go down? Oh, because I'm not in test. New share, no. Remote control, undo. Clear all dry. Okay, good. Now on the second situation is a development over what you guys did before. Color. So now you have the star, and the star is not going to be flat, so it's not flat anymore. The star is a sphere. So now your spot should have some spherical kind of a deformation because of the star not being flat anymore. So you have some elliptical thing coming up, and then it's going to be a nice circle when the spot is right in the middle, right? And then it deforms again, and it becomes oval as it goes towards the center. So what would be now your distribution of brightness over time when this star has no spot appearing, and then suddenly the spot start coming on view. So again, you're assuming the spot has an area, in fact a radius given by 1/10 of the stellar radius, and just see the effect of it. So once you figure the first solution, so how can a circle transit a bigger circle, and what effect it gives on the brightness, the total brightness of the star. Once you figure that, the rest is just to add complexity, and one is to add to the fact the star is not flat anymore; it is a sphere, and so the spot or the circle becomes projected on this circular surface. So how would you solve that situation? And then the last one is, okay, now you have done this, steering photometry, but now your view is with an angle, right? You have certain view that's not more in the equatorial. So you're not looking now on the equatorial region of the star, but you are kind of looking at any latitude. And what would be the difference now in brightness variation of the spots as you observe? In fact, better saying, so let's say the spot now you still observe the star from the equator part. Sorry about that. I think I have a better idea now. Oops, how come I not erasing? There you go. So let's keep the spot, the observer observing the star directly on its equatorial region, so the star rotates like that. But now bring the spot at a higher latitude. Let's say this is 90 degrees, this is 0 degrees. So let's go to 80 degrees. So something very on the very top, and how the change in in brightness would come out in your simulations. And if you want to play around, what if the spot is not a dark spot, but is a hot spot? And so for a hot spot, let's say for a star, so invert the temperature. Now the star is like a T-Tauri that has 4,000 degrees surface temperature in general. And you have now a hot spot that is 10,000 degrees. And this hot spot is, again, 10% of the stellar radius. And so what should be your change in flux? What would you observe? Okay. So basically, if you think about total flux, you have, let's say 90% is the one that comes from a star that's 6,000 degrees, right? And 10% for the first exercise, 10% will come from a star that is 4,000 degrees. So then you have the entire stellar surface being covered, but you have a reduction in flux because the black body of the cold spot is less intense. And so when we go to the inverse situation, now 90% of the star is of a black body of 4,000 degrees, and only 10% is from a star that is 10,000. Is a spot that is 10,000 degrees, and migrates going in and out of view. Does that make sense? Now, as I propose this project to some of you, I don't want you to get crazy. So I would like you to email me questions, because that's how we do research. I mean, you have some advisor, and that person is supposed to answer questions that you ask. So the first thing to do is the mathematical aspect of it. So how can you calculate these things? And then the second is just to make a nice animation of a sphere with spots and put the graphic with the flux kind of coming out that way. That would be cool. Does that make sense?
Yeah.
Do you have any question regarding this? Because I have another idea based on Sean's talk today. Or would you guys like to all work on this particular project?
This is pretty good.
This is okay. Would you guys prefer to work all together in this project alone, or would you like to try to have half of you work on this photometric project and the other half working on spectroscopy? It's kind of the same idea, but it's slightly different.
I think that No, this one is okay.
Okay, so then keep this project going on. The other project I was going to suggest is to create one of these p-sign profile, but why don't we do that next together, all of us together?
Okay, sure.
Okay.
Are we splitting into two groups or just everyone together?
I think let's get all of you guys working together in this project. Why don't we could do two things. One, some of you or two or three of you work on the animation, which is pretend you have a sphere. The sphere rotates, and the sphere has cells, and all the cells produce some sort of a flux, and this star is rotating, right? And so would be nice to have an animation that shows how this flux should be constant as the star rotates. So let's say pretend the star rotates 5 days. In 5 days it gives a whole turn. And let's say that the spot is supposed to survive for 2 rotations. Okay. So let me write this down. So star rotates in 5 days. Two. Just for that, the star is a black body. So this represents pretty much a T-Tori. This is a T-Tori, 4,000 degrees. And 3, the star has a spot, 10% stellar radius of 3,000 Kelvin. So it's slightly cooler. And calculate stellar flux with and without spot. And then 5 is work on projection effect, which means, so you have a star that is a sphere, so right in the limb your spot is not going to be like this, right? The spot is going to be something that is kind of oval. So how can you guys model that? If you go to Soho NASA, they might give you even some ideas on how to divide the star in cells and then work on the cells. It might be interesting to look in there. So this is basically the general idea. Oops. But you could divide in 2 groups. One group does calculations, and the second group work on animation. Or you can have one of you, working both groups. But I would like everyone to have some participation. If some of you is not participating, I could give the spectroscopy project to run, and so just email me, and then I can work with you. But let's not get together once a week. I mean, it would be nice that you guys, especially I'm not teaching now, but it would be nice if we could, exchange emails as we go, and ask me questions so we can be productive. But working animation means what? So now we have a sphere, and the sphere has a spot that is coming on view, and how can you animate that I don't know what's going on. It's funny, I'm not even touch my tablet. I have to give some distance. Interesting. Okay, now and the star rotates, and as the star rotates, how can you create an animation that have, let's say, in the left hand side you have a star rotating, and the right hand side you have flux variation and coinciding with the sports transit, and then you have another rotation and then another period of transit. And if you put relative units in here, so if you normalize this to 1, how deep this gap should be. So that is, the first group should be able to give us that, and the second group should be able to work the animation that match the calculation done. Does that make sense?
I think so. Wait, you said you also had a spectroscopic project in mind?
Yeah, the spectroscopy project is along the same line. Let me show you this. It's based on your P-sigma profile. So let's say you have a star, and the star has an envelope. And just to make it simple, so pretend this envelope, you divide this envelope in cells, and each cell is emitting a hydrogen line that is perfectly symmetric. Just make it so that so the this is centered on the transition of hydrogen line, and you have some opening, some broadening that is due to collisions in the gas, and is due to natural this excitation of hydrogen, and then you have a line that is somewhat narrow. Now imagine that every single cell is emitting that, and now you are an observer observing from here. Okay, so based on the fact the star is opaque, so what should be now it's doing again. What should be geez, I don't like this annotate. Okay, based on the fact the star is opaque, what should be the resulting profile, right? Based on the fact that every single cell is emitting the same profile, and you are adding up profiles that are centered on different locations. Now make the situation a little bit different, and that is your shell is expanding, like I show in that figure. The shell expands, and if the shell expands, let's say the shell expands with a given velocity, 30 kilometers per second. So which means every single cell is moving radially, right? 30 kilometers per second. This is the speed of the cell. But of course you're here, so you are seeing this velocity projected along the line of sight. So this is your line of sight. So it's a little bit more complex, as you can see. So so if the cell, or every single cell, is expanding at this speed, and just to make it simple, the gas is transparent, which means once this line is produced, it escapes. It's not reabsorbed by the shell, just to make it simple. The only blocking object here is the star itself, but not the gas, not the expanding gas. So if now this sphere expands, what type of profile should you observe? I mean, in the first case, you should observe a very broad profile. Okay. Should be something majestic. But if you have an expansion, now you are dealing with your P sign profile. Can you reproduce that? And then the third type of situation is now the shell is moving towards you, towards the star, I mean. And what type of profile should you detect? And then you have the inverse one. Okay. So this absorption is in the other side. So this is a project that involves to create a Gaussian emitting line, something simple, just for work, and come up with a, let's say, divide the shell. Let's say the shell has a dimension that is, I don't know, half of the stellar radius or something like that, and every single cell expands with the same velocity, just to make simple, and each cell, so you divide it in, I don't know how many cells, you can put as many as you want, as your computer can, and then each cell is producing this Gaussian profile, and if you add that up, what would be the resulting final result? So you do one, the shell is not moving. The second one, the shell expands, and the third one, the shell is falling towards the star. There's a lot of astrophysics here, by the way. Okay. So I think we should tackle the first one, the spot, going around the star. What do you think?
Sure.
Okay.
Yeah, it seems like the easiest.
Okay. Yeah, let's start with the first. You guys talk to me. Let's work together on that. You guys have the computer skills.
I think.
And the time. Now you passed the course. Hopefully everybody passed the course.
Yeah, Mr. Vijay, I think adding animation to it would be a bit too intensive and hard to do.
Okay, so we do one thing at a time. But the graphic should be simple, not so much the animation, but the graphic should be simple. You should be able to come up with a graphic explaining what happened as the spot transits the stellar disk.
I just have one more thing to say. Rohit is saying that one of his friends at Cosmos programmed a perfect eclipsing binary of two stars using Java. You wanted to know on that?
Where is it?
So Rohit said that he knows somebody who he coded a simulation of two stars in perfect eclipsing binary in Java.
Yeah, that will help.
Yeah, and we just wanted to know, what was your insight on that?
That would be great. I mean, that is the whole. I mean, it is not so much different. Instead of having a star transiting and eclipsing one another, you have one spot. So instead of having a star with or two stars with independent black body radiation, you have a spot, first of all. Second, if you have a second star, you have a moment in your orbital phase in which the two stars are detached as you see them, right? And then you have the entire brightness of the two stars. In the case of spots, the spot is always on the star; it doesn't come out. So, but the animation should be kind of the same. But anyway, so I'm not so concerned with the animation. That would be cool if you guys can do that easily with Python. Otherwise, the graphic is important. It's something you guys should be able to do.
Okay. I'll still look into the animation. I think there should be some libraries for that.
Okay. All right. That's what we do in summer.
Yeah.
All right.
Okay.
Okay. I will save this. I will create a video of this conversation and send to Sean, and Sean can distribute. Okay.
Yeah.
Oh, and next week we try CC Confer.
Okay.
All right.
One more thing about graphics. For Python, graphics are extremely hard to do.
Oh, is that right?
Yeah. You can only do like some broken implementation of Pygame and Tkinter for graphics.
Really?
I'm not even going to mention.
You could perhaps do with Excel. I mean, Excel will do it. Yeah. I mean, once the calculations are done and you can project what, I mean, you are going to divide the star in cells, and you have the spot position in phase. So let's say a phase start, phase 0 is when the spot is kind of a peaking through the stellar limb, and then the star complete. Let's say the spot is surviving for 2 rotations, which is also unrealistic. But let's say the spot survived without changes for 2 rotations. So one cycle is completed when the spot appears again in the limb, and then you have another cycle. So you should be able to give a graphic or a plot of how the stellar brightness changed in 2 independent cycles. I mean, that's the final product.
We have less than a minute left till the meeting ends, just FYI.
Oh, I missed that one. What did you say?
We have less than a minute left.
Oh, yeah. All right, so see you online. All right, bye.
Thank you.
You're welcome. Thanks for coming.
Yeah, no problem.
All right. Good job.
Yeah.